So, good morning, all, and this is Jagannathan Sundarababu, who's been assistant professor from the Department of Mechanical Engineering, right, from Sri Sastha Institute of Engineering Technology, right. And today in this webinar, I'm going to explain about the how the energy storage systems need for the energy storage systems and how this energy has been stored and what are the possible future aspects of this energy storage system, right. And there is a statistical data on how this energy storage will occur in the 2050, right? That is called as 2050, right? So, and also an experimental study on how this been energy storage is being based on the hot applications, how to store the energy, and what are the different types of methods, and what are the challenges, and what are the scopes in this energy storage systems, right? So, these are the things which you are going to see about, which I'm going to explain about today. And so, before going to the topic, I would like to introduce myself that. My educational qualifications will be coming from Master of Science from Kaunas University of Technology, which is in Lithuania, Europe, and masters. In that masters, I have done my Erasmus Mundus scholarship program, right, which is in the University of Polytechnica de Catalonia, so which is at Barcelona, Spain, and followed by that an Erasmus traineeship in the Center of Technology of Composites at Catalonia, and followed by an bachelor's of education, that is bachelor of engineering at Vidya Vikas College of Engineering and Technology, which is called as under the affiliated by Anna University. So so in this regard, I would like to show about my academic and research experience as well, right? So I worked as an research trainee at Center of Technology of Composites in Amposta, Spain, and as a researcher at Tapuza National University. And followed by in India, I've been worked as an lecturer at Madanapalli Institute of Technology, and followed by that, assistant professor at Sri Vidyaniketan Engineering College at Andhra Pradesh, and followed by that, Sri Sastha Institution, where I'm right now, and being a JRF in a DST project for a period of 3 years, right? And these are my academic and research experience. So it's been 6 years of experience, where 3 years of in teaching and 3 years in research. And these are my publications, where we so far 8 publications, which has been composed of or comprising of elsewhere Taylor and Francis, American Institute of Physics, and IOP conference series, and the International Journal of Mechanical and Production Engineering Research and Development, as well as the KTU library, right? So these are the publications, and whereas in the national and international conference, all around some eight conference papers have been there, right? Apart from this, 8 papers, publication paper. And going into the topic, which is called as an energy storage system. So, as on today, the global energy demand has been steadily increasing due to the technological development and the segment of economy of developing nations, right? So, in this, and the rapid growth of in the developing countries has been improved by the living standards of the people, right? So everybody in these every countries are requiring for this thermal comfort, where the energy storage is the main challenge for the engineers, right? So in this, for a living population, that is called as and in the living spaces, where thermal comfort in living spaces is one of the essential requirement to improve the living standards of the people. So where you can see here, and energy is being consumed from the hydroelectric power plant, which is called as in by water through the transmissions, and which is being stored in the uh, energy storage systems, and which has been supplied to the residential and as well as the industrial sector, right? So this is one form of energy, right, where the potential energy or kinetic energy is converted into mechanical energy, and then into electrical energy, and then it's finally into the residential purposes, right? So that we will call it as molten salts, that is from the hydroelectric power plant, which is being from the concentrated solar power, right? So which to discharge energy overnight, that is called the storage of energy in the daytime, and converting that energy and utilized to the end user. That end user is the residential buildings, right? So, and the other one is which is called as a tidal power plant, that is called as wind, right? So wind energy, where
Sorry to interrupt, Jagan sir.
yes, sir.
Sir, your slide got stuck in the first itself. Your PPT is in the first slide. It's not
Okay,
changing.
how about this?
Still in first slide, sir.
How
Yeah.
about now?
Now we can able to see the second slide.
Second slide. So
Here the qualification details. Now we are in fifth slide, sir. Okay, now.
okay.
Yes, sir. Yes.
How about now? It's in the fifth slide.
Yes, sir. Now we can able to see the
Yes.
fifth slide. Yes, it
Okay.
is visible.
Okay. Okay. Thank you, sir. Okay, so in this one, we have seen about the hydroelectric now. So we will be seeing about the title where the energy conversion will take place by the air and then flowing into the energy storage systems, and then from the industrial waste heat recovery, which has been converted over here by using these wind energy, right? And then which has been converted into the domestic applications, which is what primarily in the first thing which has been initiated for this domestic hot water applications is from the Sweden, right? Sweden and Denmark as the most prominent countries where the energy storage applications is being used for the domestic water heating. That is called a district heating purposes, right? So in the year of 1950s, around 1950s, they started to work on this one, which is called as energy storage for the um, household purposes. That is called domestic heating purposes, right? And followed by that, so this is the for example, you can see here, this is the district heating and cooling systems, where the thermal storage systems, which is called as a novel PCM, that is called base strain material, uh, and thermochemical based TS technologies, which has been enabled the district heating schemes, which has been completely from the renewable energy, that is called an energy from the resources, right? And this energies can be stored in the phase of ice or in the PCM, which can enable the demand of energy for district cooling schemes, right? So then this is the energy storage systems market is all about. So at the present value is all about some 10 percentage as of now, that is into 2021, right? So it might be between 10 percentage to 3 percentage, right? So the maximum market value in the year of 2025 will be the electric supply capacity will be all around some 30 billion, right? And see, these are the four prominent countries where the energy storage applications, right, which has been used the need is very high, right, and the works research works and the applications work or being very prominent in these four countries, right? So from the image from the map, you can see about what are the four countries. For example, I can say this is in the United States of India, and this has been Europe and China and Tokyo, right? So these are the four prominent research countries on energy storage, right? And US is the most market in anticipated to witness all around some over in the 2019 to 25, it will be all around some 30 billion of energy consumption, right? And in the case of Germany market, it is all about some 3% increase. And in the case of APC, that is called Asian Pacific, right, it will be all around some 7%. And the case of Japan market value, in the case of 2025, it will be all around some 65 billion, right? So these are the statistical data on energy storage systems market, right? That is which is all around the global statistics of energy storage systems, right? And in the case of thermal energy storage market, in the case of 2017, it was all around some 16 billion, and in the case of 2018 to 24, the expected rate of growth rate is all about some 18.5 percentage, and in the case of 2024, it will be all around 55 billion dollars, right? So that is the demand on energy, right? Because everybody is being in the need of thermal comfort. That is called that thermal comfort is come from the energy consumption, right? And that energy consumption is comes from the industrial and residential sectors, right? So where it has been again been used to the industrial and residential sector, and where this transmission of energy, right, the transportation of energy, this METS is the most important one, where is called transportation is very important, right? How you are going to transport from one form of energy into the other form, or from one place to the other place. For example, from the user to the heat source, right, or from the heat source to the heat to the end user, and what are the statical economic feasibility study for this energy storage, right? And the global energy storage market has been the fastest growing market by region. For example, you can see all around in the year of 2030 and in the year of 2019, right? So largest market by a region is China. And you can see all about in 2019 the market size is all about some 1,71,939.3 megawatt of energy has been consumed, and the growth rate is all about 3.3 percentage of growth rate when compared to the previous years, right? So this trend will be increased day by day, by the use of this renewable energy, right? And that is
Seven,
called
sir.
as energy storage system.
Sir, sorry to interrupt again.
Is is it
Yeah,
visible
just
now?
yeah, just now the slide has changed. Earlier it was in fifth slide. Now we are in ninth slide. Okay, sir.
Okay, so let it be. Let me go. Okay. And in the end user sector, you can see that buildings non-calculate, commercialized, and industry and the transport. The most prominent thing is all about the transportation cost of this particular energy transportation is being a main thing which has to be thought of, right? So as you see in the year 1970 to 2040, right, the transportation cost and the industry utilization cost, right? So the energy from the industries has been increased, right, because from this energy from the industries, it can be used to the domestic purposes, or to the residential purposes, for example to the smart city, right? So where the trend has been increasing day by day and the need is been increasing day by day, right? So in the case of when you go to the global GDP growth and religious contribution, right, you can see the China, India, Africa, and other Asian countries, right? So the demand has been increasing, right? So in the case of 1995 to 2017, you can see all about from the major other countries, like apart from China, India, and Africa, right, and Asia, right? Other countries plays a major prominent role in the case of this global GDP growth, right? So by use of this energy consumption, right? And also in the case of 2070 to 40, in the future, so this trend will always used to drop, because the GDP growth is been depending upon the how much of resources taken from that particular country and distributed to that particular country itself, right? So that is called as and global GDP growth on the energy sector. And in the case of fuel, in the case of transmutation of this particular energy, right? So in the olden eras like 1970, right, you can see the prominent is all about coal, right? So now it's been, you can see the graph over here, it's been the use of coal has been reduced. You can see the statics over here, right? Graph over here, it's been reduced drastically. The use of fuel energy that from the coal has been reduced. And you can see here the color which is stated as blue here, right? So which has been tremendously increasing the renewable energies, right, as a fuel, right? So as a fuel is fuel in the case of this energy storage systems, right? So from the renewable energy, right? So where you can go with the, for example, you can go with the novel phase exchange material or polyethylene glycol material, or maybe aluminum nitride. So there are many materials here. For example, HS21, HS40, all these types of materials have been available in the market, right? So this uh, increase in the, you can see this similar to the global GDP. You can see the increase in global GDP, right? So with respect to the population, right? And you can see the other graph over here. World energy consumption rises 50 percentage between 2018 and 2020, 2050, right? Which ensures that there has been it's going to be a huge demand in the energy consumption, right? And so in order to overcome this energy demand in the future, right? So there is a concept called as an mobilized thermal energy storage systems, right? So where these systems will develop the develop and to investigate the heat transfer augmented METS container, and also to design and investigate phase change material heat exchanger. So, for example, you can say heat or cold energy consumption, and also to conduct and analyze the technical feasibility, economic feasibility of systems, and to evaluate the lab scale model, and also a numerical investigation using computational analyzers. For example, you can say about the answers, or maybe the artificial neural network, right, or maybe blockchain, or machine data, right. So the first primary important thing is all about transmutation of energy, right. So here you can see you can store the energy in the night time, right, by using a fission material, and then you can transport this to a residential building, right. So the same over here from the waste heat recovery from the industry, and which can be transported to the domestic users, right. And in the case of waste heat from the solar, right, which is which can be transported to the industries, right. So this is a cyclic process where this sort of processes and renewable energy, right. So energy is from the renewable sources, right. And these are the methodology of and material identification to have a good energy storage capacity of a material, right. First, selection of material is important. For example, you have to ensure the thermal stability of a phase change material, right. So phase change is nothing but changing of space from one form to other form. For example, solid to liquid, or from liquid to solid, right. It depends upon the application, right. It depends upon the material, right. So you have to study about the properties of the particular material, and to have a characteristics of that particular material, right. So first, the initial step for this material selection is you have to go for the thermal stability is being um, uh, appropriate, and thermal conductivity is appropriate, right. And also you have to study the characteristics in the form of characteristics. You have to go with the diffraction scanning calorimetry. You have to go with the Fourier transform information study, right. And you have to go for thermogravimetric analysis, right. So these are the prominent things which will come under this material study. And then the component study, right. So component is nothing but you have to, in which component you are going to, whether it is going to be a tube, or it is going to be it is going to be a horizontal tube with a numerous number of fins, or it's going to be vertical tubes, or it's going to be a cylinder, or it's going to be a shell, right. So this study has to be taken place. So that is called as heat transfer study has to be taken place. With respect to the material, with respect to the component, or with respect to the design, right, which will give you the better augmentation. And in the case of experimentation, right, you have to do with the very lab scale model of how this what particular temperature can be maintained, and which uh, area is feasible for transporting its energy. For example, I can store a material of 20 degrees Celsius, and I can store an energy of 20 degrees Celsius, and at what place I have to transfer. For example, 20 degrees Celsius, I can heat from the some places where in India, right. So to find out that particular places and transport that particular phases temperature to the other parts, right, where the temperature is very high, right. So, and also a techno-economic feasibility study, or you have to go with a mathematical modeling, right. And finally it comes about the product development, right. So whether after completing all the study, materials, component, experimentation, and economic feasibility, and then it comes about the product development. So whether this particular material is being good to the market, right. So it's been storing good amount of energy, right. So these are the things which have to uh, and energy storage people working on energy storage has to think of, right. And so, in the case of the scope for this energy storage is all about to have a material study, to have a component design, to have a system integration, and to study the economic techno feasibility, right? For how much it can be used for commercialization. For example, a product has to be developed, right? And see here, you can see here the required technologies over here. What is the material function? How it behaves? And you have to design a heat exchanger, and what are the properties, heat transfer, thermal properties of it, right? And what is the technology which targets and then what is the product which you have to aim, right? And also what is the market need for the need, and what is the product highlights, for example, whether it will be feasible for a particular temperature, right? So you have to find the places where this particular developed product can be used, right? So these are some identified transportation energy storage systems where in future it can be incorporated, right? For example, like Forest India, Anu Ripening and Cold Storage, FMAT Systems India Private Limited, and AKS Cold Storage Limited. So these are in a simple basic scope for this energy storage systems for the research purposes, right? And so in this energy storage study, right? So first is all about an industry, right? This is an industry in Japan, right? So which is called the factory of Sanayo Electric Private Limited. So what the particular process is all about, they have a surplus condensation heat, that is waste heat, right? And then that waste heat is been converted into preheat feeding water to the boiler, and then the end user is the factory of Fukushima Sky Aluminium Corporation Limited, right? So, and the other one is on CVG plant, right, where the heat amount of unused gas from the sludge incinerator is being created, and that particular is being used to supply hot water to the absorption chiller, generating cool water to air conditioning systems, right? So, and the end user is all about civic gymnasium, right? And the sewage, right? In the case of sewage, it's been collected from Kangaya factory of Curimito Limited, which is in Okaya City, right? So which has been waste gases from the annealing furnace, and it is transferred to the heat water for the bath of employees, right? So here you can see heat water for the bath of employees, right? So conversion of waste energy into an useful purpose, that is called as for the domestic purpose, right? So which is in Shinghai factory, right? So the end user is Shinghai factory. And in the case of Transheat Germany, right? So this is a German based industry where waste incineration plants, which is called as absorption storage systems, and which has been the end user is aluminum factory, right? So these comes follows, for example, for the incineration plant, Kaga factory of Curento, which is called the Promaco Japan, right? So which is called the waste incineration plant is being waste heat recovered from the industry, and it's been used for absorption storage systems. So with to the industry called aluminum factory, right? And the other one is the transheat system, where the waste heat recovery is phase change material, by using phase change material, and being computer system study, and that particular is being used for the domestic application, right? So in that incineration plants, there is two types of container being used, right? So one is direct container, and the other one is indirect contact container, right? So where in that the waste heat has been required, and it has been transferred to the end user, right? So by the name called PCM, right? So there the study has been made on direct contact container, where PCM melts lastly in the wall, right? So in the case of conversion of energy, right? So the center part, right, the middle part of the container, or the middle part of the shell and tube will solidify as faster when compared to the uh, surface of the shell, right, or surface of the wall, right, in the direct contact container, right? So that has been study made by Wang et al, right? And so here you can see the transportation systems, right? So from the industry, right, industry wastage has been transferred to the residential purposes through a transportation systems, right? And by using the sewage, right, the wastage from the sewage has been transported to the domestic applications, right, where you can see the heat source sites, right? So this is the source where the waste heat energy, which is called which has been as an industrial waste heat recovery, right? So it's been used for a different heat demand sites, right, where the usage of thermal energy is highly needed, required. And in the case of economic study, you can see is the centralized waste heat required systems, where if you go for an economic study, you have to go for what is the production capacity. You have to know about the heat release rate. For example, how much amount of heat is being released. For example, if they are producing all about steam, right, what is the cost of it, right? So how much amount of heat can be transferred for transporting from one place to other places. For example, if you're going to transport the waste heat recovery from industry to the end user, right? So what is the distance between this end user to the heat source side, right? So if I transport for two trips or three trips, right, so how much amount of energy is required for that particular industry to the domestic or vice versa, right? So you have to calculate the cost, right? So including all this is the transportation, this is a heat release rate, right? So and the fuel price for this transportation, which will come under the transportation cost. And that particular we have to calculate with the labor cost and the production cost, right? So this is how the economical feasibility or economical study will be made. So and also this type of economic feasibility can be done using the operational cost, right? So by operational cost, for example, the operational cost will include all about the transportation cost and the cost of this heat release from the industry, right? You have to pay something for some amount for this particular heat recovery, right? And then that will be coming under the operation cost. For example, in the transportation cost, for instance, in the transportation cost will have all about cost of hiring the vehicles, how and the design of vehicles. And you have to analyze the cost of the trailers, and you have to think about the you have to include the labor cost, and you have to include the fuel cost, and also you have to include the maintenance cost as well, right? So this is the cost calculation of to have an economic study of transportation system, right? And here you can see the transport system plays a major role in economic cost analysis, right? So which with respect to the years, right? So where you can so it's from the graph it's been states that this energy storage transportation will play a major role or major contribution in the economic study or economic feasibility, right? So this the study on economical METS, that is called mobilized thermal energy storage system, we have to do about the experimental study and numerical study, and also a computational, and also an economic feasible study in order to produce to the market, in order to implement in the market, right? So this is one of the concept in the energy storage, where you can have an cold energy which is been in the hills and hills areas, right? Where you can store by using the waste chain material, and then that can be transported to the discharging station. This charging station is nothing but the residential area purposes, right? So where it can be transferred through an vehicle called as which has been incorporated with the heat exchangers, right? And in that heat exchanger you can have the energy storage material, right? And in this the energy storage in the energy storage, right? So the main challenges is all about the how much amount of time required for this charge for charging of that particular vehicle, right? Charge particular vehicle, I'm meaning in the case of particular PCM, right? Particular phase change material, right? So how much amount of charging time has to be taken place, and what is the thermal conductivity, right? So this is the two major challenges in the case of energy storage. And but the scope of this energy storage will have an heat transfer accommodation by increasing the container area or providing the fins on both outer and inner tube surface, right? So this is the scope is been how the when you compare with the previous system, how you are going to incorporate your sorry your augment your augment is nothing but enhancement of heat transfer, right? So how to enhance the heat transfer, how to uh, provide reduce the charging time, right? So these are the main challenge scope of this energy storage system. And also so in the case of normal novel phase change material, you have to think of the nano composite materials, right, in order to increase the thermal conductivity, right? So then so this is a small study of energy storage system, which is in the case of hot applications, right? So an investigation on thermal conductivity by using a polyethylene glycol is carried out. So, in this, to study the material properties and material characterization, thermal conductivity, right? Diffraction scanning calorimetry for heat rate, for heating rate, and thermal gravity analyzers for change of amount of mass in addition to the function of increasing temperature, and also the characterization of PG is also been polyethylene glycol has been carried out, right, for the by use and it's been the properties uh, to explore the property and the insight of the material by using scanning electron microscopy and transmission electron microscopy, right? So why this particular scanning and transmission electron microscopy is carried out is nothing but to study about the surface topography, crystallography of a material, right, of the selected polyethylene glycol material that is called hot applications, right, and also to study about the crystal structure. This X-ray diffraction study is also studied, right? So where you can see here. So this is a small study on hot application where six different PEGs with different molecular ratios has been taken for the study, and PEGs of six different molecular weight, in which two remains pure PEG Xi plus, and leftover that four will be the uh, normal PEGs, and this type of PEG is equipped with mixed with polymeric constituent, right, with a melting temperature, the melting temperature of 54, 49, 54, 57, 55, 62, right? These are the melting temperature of it with the heating cycle of one heating cycle, right? So where you can have an clear picture of the melting temperature of the particular polyethylene glycol, right? Where you can see that PEXI plus, right, PEXI plus, and with 3350 and 6000 will have an prominent value of comparable value of 54.47 and 54.78, right? So these two values are approximately similar with respect to the when compared to the other four PEGXA pluses, right? And in the case of DSC scanning, DSC uh, that is diffraction scanning calorimetry, right? And heating cooling rate with an active methodology is being incorporated, right? Where the samples has been taken with the different molecular weight ratio, that is all about 2.4 milligrams of weight, and it's been employed in the aluminum pans, right, where this is the diffraction scanning calorimetry process, right? So with the different heat cycling, right, heat systems with a 1.255 10 and 20 kilo Kelvin per minute be the functional parameter which has been incorporated, right, which has been a function. And in this experiment where the inert gas of argon is used to determine the flow rate of 30 centimeter cube per minute, right? So subsequently, it's been regularly monitored by regulated by Mercury and Indian standards, right? So where in this aspects, this cooling for the initiation of cooling, liquid nitrogen of 50 ml per minute has been utilized as a cooling medium, right? So whereas this six sequence of six different molecular weight of PEG with the two polymers or purity PEGs or Xi plus PEGs for the normal for normal PEGs, where you can see that in which Xi plus PEGs will have a maximum melting point of 58.15 and 49.48 degrees Celsius, whereas in the normal PEGs you will be seeing about the melting temperature of 56 to 67, 66.59 degrees Celsius, right? So just shown in the figure, right, in figure one, right? So this is the diffraction scanning spectroscopy, right, with for a different molecular weight, right? And for the to determine the phase transmission of this particular PEGs, right? So the temperature range of 90 to approximately you can say 400 degrees Celsius at 19.9 degrees Celsius per minute of heat only, right? So in this will give a transition properties for the determined curve. For example, the superior polymer like Xi plus is better than the normal polymer, where because it can give good phase transition area of polyethylene glycol 6000, which is all about 331.5 joules per gram, so which has been given a better properties with respect to the molecular weight. For example, PEG 9000 and PEG 6000. This PEG 6000 has shown better properties when compared to the other PEGs, right? So this is the graphical graphs which has been obtained by the various thermal analysis test, right? So where you can see the diffraction scanning spectroscopy of different poly 6 molecular weights, right? So where the PEG has been incorporated with a different temperatures, with the heat cycling of 1 8 cycle, right? So with a different volume fraction, right? And the heat of melting for different polyethylene glycol has been calculated for different samples, and diffraction scanning calorimetry techniques has been carried out with different ranges from which is from 90 to 200, 396.7 degrees 70 degrees Celsius, right, with a constant heat rate of 9.9 degrees Celsius per minute. And you can see the heat flow, right, transition properties, heat flow versus temperature, where the temperature drops drastically, and that is called the latent absorption rate, right? And to identify the crystallization, so these are the material study, how the material is feasible, whether it has a good thermal property, thermal conductivity, right? And in the case of crystallization study, right, so crystallization formation is stronger when the molecular weight of PEGs are higher, right? So when you increase the molecular weight, right, the crystallization has been stronger when compared to the 3350 Xi plus uh, molecular weight PEGs, right? Meanwhile, this crystallinity degree has been calculated by using the formula, using this formula, right? So the main parameters are heat of melting, percentage of crystalline polymer, and the heat of melting of polymer, right? So these are the two main parameters for this calculation of crystallization. And you can see here in the table 3 and table 5 the results of crystallinity, right, where the PEG have a diverse molecular weights, right? So as it known that the molecular weight of PEG increases with results in increase in the development of crystalline phases, which is associated with the lower segmental mobility, right? So and feasible, right? So these are the crystallity studies, where from the studies it can be clear that so when there is an increase in the molecular weight, the heat of reading is good, and it is a good better properties when compared with the lower molecular weight, right? And this is the preparation process, where this molecular weight with the different pHs has been prepared, right? It's been taken, and with this heating rate of 2.5510, where you can see that there has been a melting point has been increased, right? Here it is all about 61 62 62 and 234 it approximately ranges about 234 is the constant temperature within the melting rate, right? So here you can see how this personally forces be enforcement of this experimentation has been carried out for temperature versus heat flow rate, right? So the effect of heating rate of melting temperature, as well as heat of melting, where you can see 1 degree Celsius, 2.55 and 10. So this is called a variation in the degrees in the uh, use. So where with respect to that the material transformation takes place, right? uh, and this is called as a thermal stability study, where molecular weight versus solidification temperature, right? So this from the graph it is being clear that when you increase the molecular weight, or when you increase the molecular weight, right, so the pHs versus the solidification temperature also rises, right? So solidification temperature has been raised. So see here from the graph, from the table, right? So for example, a normal PEG, sorry, XI plus PEG with a 3350, and PEG with the 20,000, where you can see the temperature of solidification rises, right? Not drastically, but it rises, right? So heating rate is all about 5 Kelvin per minute, right? So heating rate for this particular material, right? And so the next one is thermal gravity analysis has been taken by using this thermal uh, gravity analysis with samples of 6 to 515 mg is being weighed and it's been employed in platinum plates, right? So with the heat rating heat at about 900 degrees Celsius at a 10 degrees Celsius per minute at a rate of under nitrogen purge, right? So under that, the nitrogen is all about 60 ml per 60 milliliter per minute, right? So this is the sampling process, all right? So where degradation process has also been carried out to find the thermal stability, right? So which eventually to study the thermal stability also we had has to be carried out, right? Where the polymer melting or degradation should be before 200 degrees Celsius, right? So from this study point of view, right, TGA study, all right, it's been shown that the thermal decomposition temperature ranges will be 176 degrees Celsius to 437 degrees Celsius of PEGs, right? So this is the range of thermal decomposition, right, of PEGs, polyethylene glycols, right? This is nothing but polyethylene glycols, right? So the decomposition temperatures will be takes place largely where the molecular weight than the smaller molecular volume of it, right? So from the this TGA, it has been shown that the PEG samples remain thermally stable in heat capacity measurement region. So below 120 degrees Celsius or similar, right? So it becomes stable below 120 degrees Celsius. So this is the thermal gravity analysis, right? The thermal gravity analysis decomposition curve, right? Where you can see all about some 397 degrees Celsius, the temperature drops, right? So this has been characterized for different PEGs, right? And in the case of characterization, thermal transmission electron microscopy is being carried out, where you can see that different microstructure. For example, we have taken a prominent structure which has been 3350 and 6000 xi plus, right? So when you compare with this two molecular weight of 3350 has shown a better property, right? Such as voids like air bubbles, right? So you can see an air bubbles over here. So with the nanometer range of 200, whereas in the 500 nanometer array, right? So it's been evident that the voids are mean much when compared to the 6000 60,000 xi plus, and correspondingly in the xi plus 60,000. So the voids, that is the PEGs have shown voids like bubbles over here, and which has been shown in the figure, right? So where this both 3350 and XI plus 6000 60,000 PEG as an air bubble, right? So this is nothing but the air bubble which has been observed from the surface topography, right? So as from the transmission electron microscopy results, right? So it has been clear that there is a potential voids which may be caused by heating rate and heat of fusion of particles, right? So these are the two defects. These are the two possible ways of uh, this formation of this voids, right? Maybe the heating rate or maybe with the heat of fusion of particles, right? So when you go with the scanning electron microscopy, right? See the other topography to identify the topography of the PEGs, right? So here you have PEGs or been examined by using the scanning electron microscopy technique, where samples of higher molecular weight have enormous amount of small sphere-shaped crystal arrangements, right? So molecular weight is, if the molecular weight is higher, you can see an enormous amount of small sphere-shaped crystal structure, and also fusing of or impinging of material has been taken place, right? So from the figure you can see this is called a fusing, or being you can say as impinging of on the other neighbor particles, right? So so that could pave the way for the formation of multi-layered lamellar structure, right? You can see the lamellar structure over here, right? In the case of scanning electron microscopy analysis, right? And as a result, it has been clear that an increase in the molecular weight of the PEG, the temperature of solidification increases. The same criteria which we have been seeing in the diffraction scanning calorimetric, right? So this is the X-ray diffraction curve, right? Where you can see that. the intensity is been increasing, right? When there is an increase in the intensity, the polyethyl glycol with a higher molecular weight has shown an prominent way of, or we can see an enhanced way of thermal conductivity, right? So you can see that xi plus samples have less intensity, right, which is in the range of 3000 31,033.33 for the xi plus of 33550, and 41 4,160 for xi plus 6,000, right? So these are these two samples have been shown better properties when compared to others, so that we have taken the this property for the for the next level, that is called as, which has been these two proper materials, polyethylene glycols, can be incorporated into the heat exchanger, right? So for heat storage application, right? Which has been that heat has been recovered from the waste heat recovery, right? For example, you can see a planes where an industry which can produce a high amount of heat energy, right, waste heat, and that can be utilized in the form of stored in the case of PEGs, and that can be transported to a vehicle where the heat energy is required. For example, heat energy requirement is in the case of district heating, right? So district heating is nothing but for water heating purposes, right? And the cutting edge effect of this thermal analysis, thermal stability, and phase change property of PEGs with the different molecular weights has been shown that this PEGs with 3350 and 3 and 6000 can be used for the potential use of energy storage applications, right? So this is the case of in the case of future energy storage applications, energy storage sector. So you can see here, right? Energy can be transmitted through a pipelines, right? So, and it can be, you can see here in the vision of 2050, right? So like the phase change material, incorporation of phase change material, or can be in and HS something else material, that is called the energy storage material, can be incorporated over here, where the energy requirement is been high, right? So, and also by using this type of renewable energies, the carbon footprint can be reduced, right? That is called zero emissions energy systems by 2050, right? So this is the small statistical data of energy storage, where we have seen already, like the energy user sector is been increasing day by day, right? End user is been been increased day by day. For example, the annual energy consumption is increasing in fast growing economies, or for the developing countries, especially in India and China, right? So, according to the statistical review of World Energy 2019, right? So, the energy demand thirst quenches through non-renewable resources as an indicator for the need of industrial waste. Okay, so industrial waste, or maybe the industrial waste heat requiring. So, so, so from this graph, you can see that the increase in the uh, trend shows that the energy sector will play a major role in uh, the living spaces, right? So these are some references from the where the sources been taking place, and thank you for your time with your for your patience time, right? So if there is any doubts, you can ask me. So else I can close the session.